Hello, welcome to Light Waves. I am Laura Lewis. This is part of the Key Stage 3 and up to Key Stage, beginning of Key Stage 4 GCSE Physics. Let's get on with the lesson objectives, learning objectives. I'll change the slide. So, first learning objective. So, understand the characteristics of light and the electromagnetic spectrum. Number 2, describe the behaviour of light as a wave, such as in reflection and refraction, and how to answer questions on light and its properties. So by the end of this, you should be able to answer questions based on light and its properties. Okay, so looking at the features of a wave. Okay, so a wave has an amplitude, a frequency, a wavelength, and a period. So let's have a look at these in more detail. So the amplitude. So this is called a transverse wave. So light's a transverse wave. So there'll be other videos on longitudinal waves like sound, but this is a transverse wave. Okay, so the amplitude is how far the peak, so this is a peak labeled there, the peak is of a wave away from the middle or the zero line, and the peak is the highest point, okay, above the line. And the trough, so it's the same spelling as what a pig eats out of, is down here. So peak and a trough. So the amplitude is this line here. So we draw a line along the middle with the zero line, okay, and it's the distance between peak and the middle line, or a trough and the middle line. They are the same. Okay, so one wavelength is a distance. It can be measured 3 different ways. So it can be measured peak to peak, like shown here. It can be measured trough to trough, or it can be one peak and one trough. So they're all the same distance. Okay, so light acts like a wave and has these properties. So for a wave to move, it needs to be displaced from rest position. Yeah, the zero line can also be called the rest position. So the top of the displacement is called the peak, and the bottom is called the trough, as we just said. Okay, the period, okay, is how long it takes one complete wave to pass past a point. Okay, so how one complete wavelength to pass a point, and the frequency is how many waves are passing per point per second. Okay, so light belongs to a family of waves called the electromagnetic spectrum. They're also known as electromagnetic waves. You don't have to know this stage, but it's interesting anyway. They're called this bit here. You need to know this bit, but not this bit. They're called electromagnetic waves because they're made of 2 components: an electric component and a magnetic component, and they can be polarized. We don't need to know. I won't talk about any more about that. But that's why they're called it. But we're just showing you here, there's 2 waves here, and this wave, okay, these are both measurements of wavelength, okay, so they're measuring peak to peak here, so it's easiest to show. And this one has a longer wavelength than that one, so that's how we measure the wavelength. So, in a vacuum, so a vacuum is completely empty space. There's lots of words today into waves. So in a vacuum, so completely empty space, all electromagnetic waves, including light, and others will meet in the next slide, travel at the same speed, 300,000 kilometers per second, also known as 3 × 10⁸ meters per second. Don't worry too much if you don't quite understand. It's called standard form. Okay, be introduced in maths to it, but it's also, you need to know they all travel at the same speed. Okay. So because there's no particles for the waves to collide with. They do travel different speeds in water and glass and things like that we'll talk about, but in the vacuum of space, okay, in a vacuum, empty space, they'll travel at the same speed. Okay, so these are electromagnetic waves. They're very interesting group of waves. Okay, so light, or visible light as we know it, is in the middle. Okay, and we just talked about the wavelength, so we'll talk about that first. Is that you can see at this end, these waves have a longer wavelength than at that end. So radio waves have the longest wavelength. Then it goes to microwaves. So you think, that's like cooking. Like, what are you cooking? It's called a microwave oven, and it uses microwaves. Okay, it's a microwave oven, is thing that's in your kitchen. Infrared. So we can't see that, but we feel it as heat. Some animals, like snakes, can see infrared. Visible, that's what we see with. Ultraviolet, yeah, you may have heard that from the sun. Okay, that's what it causes sunburns, ultraviolet. X-rays, so for medical imaging. And gamma rays, okay, some radioactive sources. So, but these are all parts of the family of light, okay, and they're all waves. Okay, that's the important bit here, all waves. So let's have a look a bit more detail, a little bit more interest here about how big these waves are. Okay, so radio waves can be nearly a kilometre long. So their wavelength can be nearly a kilometre, so the size of buildings. Microwave centimeters, so kind of human size between radio and microwave. Okay, infrared, quite small. Visible, this is protozoa. So visible wavelength light is actually tiny. Even so we can't really measure the wavelength by eye. That one, ultraviolet. Okay, molecules, X-ray, atoms, gamma ray, atomic nuclei. So here we see the frequency. So how many waves passing a point per second, and gamma rays have the highest frequency and radio have the lowest frequency. Okay, this is an interesting thing about the temperature at which radiation is the most intense. Okay, that's quite interesting actually. It says about 100 Kelvin, 100. It's up to, this is it's quite extreme, 9,007. The reason why this is for stars, this one, this it looks like a thermometer for stars. As humans, we're kind of obviously along the cooler, obviously hotter than this and cooler than this. So actually we emit in the infrared. Okay, animals and humans emit in the infrared. That's why we feel it's heat. Okay, that's why animals like snakes hunt using infrared. They can see like mice and things that they eat in the infrared. Okay, so this is a bit more detail on it. So radio microwave, so wavelengths approximately 10 to the -5, 10 to the 3, not visible. So we can't see radio microwave, what that's saying. Okay, or infrared, but some animals can, but humans can't. Visible is the only thing we can see. We can see a little tiny bit into the ultraviolet, but not much. So these are visible, and luckily for us, it's called visible light. It's nice, it's easy to remember. Okay, X-ray and gamma ray we can't see either, or ultraviolet. We can't really see most of the ultraviolet. Again, some animals, like bees, can see ultraviolet, but not humans. Okay, it's just visible. That's a good name for it. Okay, so this is a good. I'm going into more detail about the uses in a minute, but this is a good summary of the uses. So I'll go into more detail on the next slide. It's a bit more interesting. So this is a video, obviously, so you can pause at any point. So sometimes I go through a little bit quick. So radio waves. Okay, so radio. So mobile phones use radio waves. Okay, communications like satellites. Some satellites use radio for picking up television signals, and also radio and TV broadcast. So that's for the TV broadcast, and the radio you can listen to uses radio. It's quite an easy one to remember, that one, isn't it? So the EM spectrum is not a difficult thing to talk about because it relates quite heavily to real life. Microwaves, again, cooking food. Might know it as. I mean, that person got pizza, doesn't cook that well. I would recommend putting that in the oven. A little bit of a tip there. But you never put chocolate in the microwave. The reason why is that microwaves work by heating up the water in food, and all the chocolate will do is burn. Okay, so it actually heats the water in the food. So satellites also use microwaves to communicate with the Earth, like very high satellites, and to communicate with each other. And radar uses microwaves too. Infrared, so that looks like I'm hungry now, looking at that chicken. Okay, so the oven uses infrared. So remember, infrared we know it's heat. Sometimes you get infrared heaters. Sometimes that's all you can buy from shops and things. Remote control uses infrared. Okay, that's why it's called line of sight. Okay, infrared. Thermal cameras. I said about thermal cameras. Some animals can see in this. Okay, in this wavelength, but we have to use a thermal camera if we want to see like that. Visible light, okay, we've got the human eye there to help. Obviously our vision, our eyes use visible light. Lights, obviously, visible light. Cameras, okay, so sometimes, yeah, so it's illuminated cameras. When you get that in an exam, you might get something like, say, 2 uses, and you think, well, seeing a lot of cameras use it, because you get other cameras that are not visible. Ultraviolet, okay, so tanning beds, which are not very good for you. Ultraviolet damages your skin, we'll talk about later. Checking forged banknotes, so if you put a real banknote, this is £20, under this UV light, then it'll sort of illuminate, okay, because it's the way it's made. If it's fake, you won't have that, okay. And sometimes you might see a black light at some parties and things, or events you go to. That's an ultraviolet light, and it makes things appear to glow. An ultraviolet light there. And also, I think another ultraviolet one is if you have gel nails, you also have a UV light. I've actually got one. I use it quite a lot, ultraviolet. Again, don't look at it directly, because also it can damage your eyes, ultraviolet. That's why I think this person's got like sort of goggles on. X-rays, medical imaging. So this is an X-ray for someone's hands. Okay, and this is a CT scanner. So this is like a 3D X-ray, the CT scanner. Gamma rays, okay, they're used for lots of things. They're medical imaging. Okay, so this is using gamma rays, medical imaging. Radiotherapy, okay, so treating cancers, and also sterilizing equipment. So some surgical equipment is put in this sort of looks like an oven thing, and uses gamma radiation to sterilize it, which means it kills the bacteria and pathogens on it. Okay, so this is going over, and again, another overview. So high frequency to low frequency, okay, and the dangers. So we'll talk about it a bit more next slide as well. So gamma rays, cell mutation can lead to cancers. X-rays, cell mutation can lead to cancers. That's why you don't want too many X-rays. And doctors have to be very careful with gamma rays too. Ultraviolet, again, skin cancer. Okay, that tanning and things are not putting enough, so you can get skin cancers. Visible light, okay, not really that many dangers unless you don't look at very bright lights. It can hurt your eyes, but that's a sort of a sensible thing. Just don't look at really bright lights. Infrared, yeah, burns the skin. So sunburn, ultraviolet can cause that too, but burns. Skin microwaves, very few, really actually to humans. And also radio, very few. Again, sometimes that can cause internal burns, a microwave. Okay, so we've got some signs. Yeah, damage to eyes is UV, damage to eyes. Some skin damage, yeah, sunburn, skin aging actually as well. X-rays can lead to damage to DNA, and that can lead to cancers. Okay, we'll talk a little bit about reflection and refraction. So reflection, okay, so light, all forms of light, if all forms of EM spectrum can reflect. So you see here, there's a perfect reflection of the mountains in the lake. Okay, so this is caused by, this is a diagram, so the incident rays are right, and this is a mirror, it's a scientific way of drawing a mirror. So the incident ray comes in, and that's a reflected ray. And the angle which, this is called a normal, so this is a line that we draw at right angles to the surface of the mirror. So the angle of incidence and the angle of reflection are the same. So as you can see here, the top of that mountain lines up with that. Okay, in reflection, light travels in straight lines, and it's reflected back. So there will be more videos on reflection, okay, that we're going over today, but those are the same angle. Refraction, so you can see this man's head has been, looks like it's separate from his body, but that's caused by refraction, which we'll talk about. It's quite a fun thing. Okay, examples of refraction. So if you put a pencil, I wouldn't put a pen in, come up with the pen, but a pencil is fine. You put a pencil in a glass of water, it looks like it's bent. So like the man's head, it looks like it's bent. Okay, it's refraction. It's bending the light, which we talk about. There's a cat. Okay, so you can see you can see the cat's the image of the cat's face has been bent a bit there. And the arrow tricks. If you draw an arrow on a piece of paper and put a glass of water in front of it, it would look like it will go. It would look like it's bent. It would look like it's pointing the other way. So you can try that at home. That's a nice safe experiment to try at home. Okay, and also in glasses, refraction. rings. Okay, the reason why diamonds are sparkly is because of refraction. Okay, and like nice patterns in oil with refraction too. That's some of refraction, and a rainbow is refraction. So what is refraction? We'll still get onto it. Oh, we'll talk about that in a moment. That picture, and that's refraction. That's what we'll talk about that. Okay, so refraction occurs when light passes from one medium. Okay, a medium is something that light passes through: glass, water, air. So air and water we've got. This is like the top of the water. But yeah, medium, plural, more than one, media. Okay, yeah, boundary, the two surfaces meet, the medium meet. Normal, so we just draw a line in and we draw it. It's not actually occurring, it's to draw it to help us. This is going to be, so what's happening? The light comes in here and it's bent. Okay, so refraction is the bending of light. So at this level, we just need to know refraction is the bending of light. Okay, that's the incident ray and that's the refracted ray. So refraction is the bending of light going from one medium to another. Angle of incidence, that's the angle. Theta is often given by angle. And refracted ray, angle of refraction. Okay, so reflection of these reflecting light. Refraction is where light bends when it meets a different media. Okay, so that's sort of the basics of light. We'll go over other things in the videos. I hope to see you in a different video. Thank you and goodbye.